Good morning, everyone, or good afternoon, and welcome back. Thank you for showing up for your learning. We are here taking a look at doing some reading from the textbook. There's some great sections in there with excellent diagrams to get us started for looking at similar triangles. Similar triangles we're going to see have to do with the triangles that have the same angles and the same ratio of side lengths. The side lengths aren't necessarily the same, but the ratio between the side lengths will be. Okay, and then I'm going to challenge you to take a beautiful note on all this material, and you can feel free to click there and go into shared notes, put your name here, and then put a screenshot of your note, or maybe you just take a picture and put the pictures of your notes in there, and we'll have points for the most beautiful note or the most effective organization of that. I could certainly use that for your learning skills and even for your marks if you're having some trouble at any point during the course. I can boost you a bit for doing that. Okay, so also all of the textbook readings that we're going to look at are available there. So let's get started. So when we have a new topic like this, it's good to take a look back at material from before. We want to remember these types of patterns, okay? Where if we have two straight lines crossing, the angles that are opposite one another will be the same. That's just a geometric fact. If we have an isosceles triangle with two sides that are the same length, these two angles will be the same. Supplementary angles. If an angle is supplementary, that's by definition that those two angles added together equals 180 degrees. 180 degrees is a straight line. If I turn myself around 180 degrees, you see the back of my head. So that's supplementary. All right. These two angles add up to 180. Okay. So if that one was, so we can create some equations from situations like that. Let me show you. If we have a situation like this, where I have this straight line and that straight line, and I say, well, this one is 150 degrees. Okay. Well, then this one over here would also be 150 degrees. All right. And then if I said, find X, it was a typical mathy type question, or find X. Okay. Well, X, it's easy to find because you can notice that these angles are supplementary. They add up to 180. So I know that 180 equals 150 plus X. And I can put in my degrees there. And then I just do some quick rearranging to solve for X. And many of you are screaming at your screen, Mr. Jennings, go faster. It's 30. Yeah, okay, it's 30. All right, so then this is equal to 30 degrees. Oh, and this one over here, opposite, would also be 30 degrees. Cool. Okay. And you can also feel free to watch me at a 1.5 times speed or 2 times speed if I am going a little slow. Complementary angles, that's where we take 90 degrees and we cut it up, okay? Where these two add up to 90 degrees. All right. Last idea here is that the sum of the interior angles of a triangle is 180 degrees. Doesn't matter how I draw the triangle, the angles always add up to 180. Let's take a look at what that looks like if we have some mini equations that we need to solve. If I have this triangle here, pion, 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 and some of you are saying that's not a triangle, you're right. But once I label it as a triangle, it kind of is. So let's say that this one looks like about 25 degrees. All right. And we'll say that that one is 85. And then I say, find me this angle theta. Theta looks like a 0 with a line through it. Okay. So there, I know that 180 degrees is the total of all of these. So let's write that down. 85 plus 25 plus theta equals 180. All right, let's do some rearranging. Well, first I can simplify. This is equal to 110 plus theta. That's 25 plus 85 is 110. Last time I checked. Then I subtract 110 from both sides. 110. And that gives me 70 degrees is equal to theta. Okay, so that's how we can determine what that angle is. Keep going. All right. Now, when a transversal crosses parallel lines, many pairs of angles are related. These are really cool and good to remember. A transversal just means some line that crosses two parallel lines is called a transversal. So when there's a Z pattern, these two angles are the same. The reason is, well, they're parallel. These lines are parallel, so the angle that's created there is the same as the angle that's created there. The corresponding angles are the same. That's we sometimes think of that as an F pattern. So you can see the letter F there. You can see the letter Z there. The corners are the same. And also, say this angle here would be the same as that angle there. That's what's being shown by the F pattern, corresponding angles. And then co-interior angles. These are supplementary. These add to 180. Okay, so let's take a look at where we might see those. Let's say, let's use a more of a like a typical type of question. Here's a plane, and you draw a plane like this, everybody. You draw a plane as a stick with two triangles on it. All right, so there's a plane. All right, there's the cockpit. And it looks down and it sees you, isolating from your friends over here. And the plane notices that it has to look. Here is the line of the horizon, okay? And that's a line parallel with the ground. You're standing on the water for some reason. You're amazing. You're out there on Georgian Bay, standing on the water. That's parallel. This is looking out along the horizon, a line parallel with the ground. And the pilot notices that he's looking down at you at 20 degrees. So we would say, what angle are you looking up at the plane at? Well, that's the Z pattern. Okay, that would be 20 degrees also. We're going to be using that through trig and other things. So these are important patterns to remember. We might also say, what is this angle? Well, we could find it out a couple ways. We could say that it's supplementary with this angle here. And so this angle would be 160 degrees. Or you can say, well, I see a C pattern here. I have two parallel lines, and they're crossed by another line. So this angle here, if it's 20 degrees, that's really not, but it's maybe closer there. Then this one, if I said find me x, then you would say 180 is equal to 20 plus x. X therefore equals 160. Okay, because the C pattern tells me these two angles are supplementary. They add together to give me 180. Let's keep going, Mr. Jennings. All right. So if we wanted to find these unknown angles, well, let's do it. Oh, hold on. I have students showing up.
Hello.
Okay, let's carry on, everyone. So we're back in here. So let's copy this diagram over, and we'll find all these unknown angles. All right. So what I'm going to do is remember it and then copy it. So we had here two parallel lines that were crossing. And then this one was divided into two here, like that, where this is angle C and this is angle C. This is 50 degrees. And then we had, this is angle X and angle Y, I think. Let's just go check. And an XCC. Yeah, that's exactly the same thing, just different letters. All right, so now let's find all of these. First of all, we know that C plus C equals 50 because these are opposite one another. So C plus C equals 50. I could also write 2C equals 50, and then I divide both sides by 2, and that gives me C equals 25 degrees. So that's C, 25 degrees. X and Y, well, I can see that 50 plus X, these are supplementary. They add up to 180, so I have 180 equals X plus 50. Subtract 50 from both sides, gives me 130 equals X. Okay, so let's put that on there, 130. And then we know that X equals Y, because they're opposite angles. So y equals 130. Done. All right, so that's how you would approach questions like that, where you have to solve for all of these angles. And then over here, we notice that if this is a right angle here, then that one is a right angle. and that means E and E are a right angle. So E is 45 degrees. And then we also need to find R. 52 plus R is 90. So R would be 38 degrees. Okay, so you can try some of these yourself and such. All right, let's keep going. Um, okay, cool. Let's keep going. Now the Pythagorean theorem. This is important to review for our unit today. When we are looking at a triangle that it has a right angle in it, we can only use Pythagorean theorem with right angle triangles. Next unit, we're going to learn what to do when they don't have a right angle, and that's your more advanced trig unit. Next unit. But when we have a right angle, we can use Pythagorean theorem. The longest side is called the hypotenuse. C squared, its square will always equal the square of this plus the square of that. It's very, very cool. So if we have a ladder that's 6 meters long, and we want to know how high up the wall that ladder will go, if the base of the ladder is 1.4 meters from the edge, well, we can use Pythagorean theorem to solve that. Blah, blah, blah. That's how you do it. Let me show you. I'll take you through it. 6 and 1.4. Okay, so here we go. Okay, here is our ladder. It's a blue ladder, and it sits going up this way. It's 6 meters long. And this here, it's going up the wall. The wall is also blue for some reason. The wall makes a right angle with the ground. That's the thing with right angles. They show up an awful lot. They show up in XY axis and XY coordinates. The Y and the X are at 90 degrees to one another. And gravity generally makes a 90-degree angle with the ground. Okay, so that's why our walls go straight up and they make 90-degree angles with the ground, unless you live on a hill. All right, so anyway, this is 6 meters long, this is 1.4. And we want to know how high up the wall this ladder goes. So we would do it this way. We would say, well, I know a squared is equal to b squared plus c squared. Okay, so it's this side, and this side. All right, so let's go ahead and we'll set that up. 6 squared is equal to 1.4 squared plus x squared. All right, we have to have our unknown over here because it's one of the legs. This is a hypotenuse. These are the legs of the triangle. They're the two shorter sides. Okay, they belong together on this side, and then this one is on that side there. So now let's do the math. This is 36. 1.4 squared is like 2.8, something weird. So you go and you get your calculator, and you go 1.4 squared is 1.96. Yeah, not 1.8 something. I should know that. I'm going to memorize that soon. 1.96 plus, well, we still don't know x, so we still know x squared. Now, we're going to go ahead and subtract 1.96 from both sides of the equation. And we see this is going to be awfully close to 6 here. So 36 minus 1.96 gives us 34.04. Okay, prove it to you. Minus 36 equals, but I did it in the wrong order, so it's positive 34.04. And so now let's flip the sign. And then now I have 34.04 is equal to x squared. How the heck am I going to find x? Well, my now inverse operation is to take the square root of both sides. Okay, so let's take the square root of this. 5.8. I told you it's going to be awful close to 6. So then we have down here, this is 5.8 equals x. Pyo, we're done. All right, let's see if they got the same thing over here. They did 5.83. They kept 2 decimal places for some reason. 1 decimal place would be fine. They see in their answer 5.8. Why did I say 1 decimal place? Because the question gives you 1 decimal place. So that's how many decimal places you should report in your answer. All right, so that's using the Pythagorean theorem. Now, if we wanted to find the unknown side lengths here, I would take the square root of 15 plus the square root of 11, and then that would be the x squared. and then take the square root of that. Use the same thing. So let's go ahead and do that. So now we have a triangle here. Whoa, that one is 15 long. Wow. That one is 11. And that one is, just remind me. Oh, I should remember these things. 11, 15, and then x. Okay, so this is 15. This is 11. This is x. So I know that x squared, because that's the hypotenuse, it's the longest side, the side that doesn't touch the 90-degree angle. X squared is equal to 15 squared plus 11 squared. 15 times 15 is 225. It's Mr. Kujala's math room. And then plus 121 is 11 squared. Okay? And that's still equal to x squared. Right? Just bring everything down. Notice my equal sign just comes down. Just write one equal sign per line. Okay? X squared equals 225 plus 121. That is 346. 346. So now was the last thing we have to do is take the square root of both sides. It's an inverse operation. So go ahead and in your calculator, clear, 346, and then you can take square root of that, 18.6. And another thing that you want to do, okay, and this is very important. I'm going to mention this in the morning meeting. I'm going to make a note to mention this in the morning meeting. 18.6. Important thing to do is then to write it on your diagram and say, does that make sense? Could I have a triangle with a side length 15, a side length 11, and a side and the hypotenuse, longest side, 18? And yeah, it totally makes sense. It feels right. In fact, before you do these calculations, working from this equation to this answer, you should guess. And you should say, well, I know that this could be at like maximum 26, because that would be 15, that would be 11, and that's the longest I could arrange those sides. That would be 26. That wouldn't be a triangle, right? As soon as I prop it up, like 15, 11, this gets shorter. And then if I prop it up all the way, so it's 15, 11, I expect it longer than 15, but way shorter than 26. So 18 fits the bill. You want to do these guesses so that you build your intuition for these types of problems. Okay, so then this connects to our xy plane and slope. Okay, slope is where we get these triangles, and we've been using rise and run. So here's rise, here is run. Here's a triangle that runs 80 while it rises 40. Okay, and then the slope of that is 1 over 2, because this reduces to 1 over 2. And we can express that as a fraction in lowest terms. So if we wanted to find the slope of this ramp, we would say 20 over 30 or 2 over 3. The factors 10 come out and cancel. So this is slope 2 over 3. And this one is half over 2.2. So there, I would just leave it as 0.5 over 2.2. Okay? Or you could say 5 over 22 if you wanted to not have decimals in your fractions. Okay, so that's that page. Let's keep going. And then another thing we're going to be working with in this unit, particularly with similar triangles, but trigonometry is all ratios. Ratios are very important. So here you have the picture of a flea. Okay, the image is much bigger than the picture. So the actual size, if the actual size was unit 1, then the image size is 30. What that means is if you had actual fleas, you could line up 30 fleas from like the tip of the nose here to the butt, if you were lining up the fleas nose to butt. Okay, if you were lining up fleas nose to heel, then you would have 30 fleas along their nose to heel. Okay, that's a ratio, and you can visualize it there. Um, and if we wanted to say, well, we could find the actual length of a flea by measuring this picture, and you can go ahead and measure it in your textbook. It's 45 millimeters long, 4.5 centimeters. So then you would multiply this by the ratio to find the actual length of a flea, 1.5 millimeters. Okay. So these are ratios that we are going to be using throughout the unit. And then we're going to be applying those to triangles next. Okay, so geometric shapes are often used in construction and design. Not only are certain shapes naturally pleasing to the eye, but they also often are useful for their structural properties. So if we take a look at this shed, what geometric shapes can we recognize? Well, There's rectangles, of course. The bottom could be like a rectangle. The doors are rectangles, and rectangles are really useful. Doors, windows, pieces of paper, this little box that I'm speaking to you through, rectangles are everywhere. And if I divide a rectangle in half, like I go across the rectangle, there's two triangles. So I can see some triangles in there. And I could divide the roof up into triangles as well. This would be one triangle, and it has a hypotenuse and a run and a rise. And this is a triangle here, and it has a run and a rise. Okay, so I could divide this, like, it's not circular, but it's angular roof into four different triangles. And then I would have a rectangle in there that's not included. Okay. And then there might be several figures that are congruent and several figures that are similar. So what do these definitions mean? If something is congruent, it means it's the same shape and it's the same size. So if I look at this one here, this triangle, or let's say these windows are congruent, right? If the ratio of the sides of the window were the same as the door, then they would be similar. Similar figures have the same shapes but different sizes. Oh, I have someone who's arrived to chat. Okay, let's keep going. So, how can I recognize similar and congruent figures? Well, you're going to look at it and you're going to say, um, first of all, like this one here, it looks very similar to that one. In fact, they're the same shape, they're the same size. So you could measure this with a protractor, find its 90 degrees. You can measure this length with a ruler, find its length. You can measure that length with a ruler, and then you can measure this angle or that angle, find that they're also 90 degrees, and then measuring this with a ruler, find that they're the same size. Okay, that's how you can prove congruence. That's how you can prove that two things are the same. If they're similar, on the other hand, let's say I wanted to prove that this window was similar to the whole door that it's in. Well, then what I would want to do is prove that the ratio of the sides, long side to short side, is the same as the ratio of long side to short side in here. Okay, so um, yeah, so let's go ahead and take a look at these triangles, because we're going to be focused on triangles this unit. So let's get on to this example. And this is a great one. You can use this trick to measure trees and the height of any object in your environment if you just have another person or a meter stick or something with known height. Okay, so here, if we notice, all right, that this triangle here shares an angle here, it shares this angle, and it shares that angle. Okay, so let's go ahead and we're going to draw this and make some notes about it. So we've got a situation where we've got a tree. So we're going to draw our tree in green. And here it is. It's a very narrow, very tall tree. All right. And it has a little trunk. And it makes it, and we're working, we're not on a hill here. We're working on flat ground. All right. And we have a friend of known height who is also purple. So I'm just going to draw this line here because I need this to be right. So then what you do is you put yourself here. You get down there on the ground and you're going to look from this angle, okay? Right level with the ground. You get your eye right on the ground, okay? And you maybe have to take it out of your head and put it on the ground to do this. Like you could do this with a camera, okay? Put it on the ground, not your eyeball. I'd not tell you to do that. And then you get your friend to stand in such a way that their head just touches, when you look there, the tip of the tree along your eye line. All right. And then let's say your friend is a little short. They're 1.5 meters tall. The tree is X meters tall. We're going to find X. Okay. We know that the tree makes a 90-degree angle with the ground. Its height is 90 degrees to the ground. And your friend is going to stand also straight up. So they're not going to be leaning over looking cool. They're going to be standing looking normal at a 90-degree angle there. Okay. And then we know that this angle here, it doesn't matter what it is. We're going to call this angle theta. Okay. This gives us two triangles. And in these situations, it's helpful to draw the different triangles. Okay. We have this triangle, which is angle theta. And we know that this side is 1.5 meters. This is the triangle that's created here by your friend in the ground. And we can measure this very easily, this distance here, right? Much easier to measure here to here and here to here than it is to climb the tree like a squirrel and somehow dangle something hanging there.
Oh yeah. Hello.
I'm popular today. It's delightful. Okay, where were we? No, we were not looking at trigonometric functions. We were looking over here at this triangle. Right. So let me go find it. It's down here. That was this grade 11 stuff. Okay, so we know this triangle we can measure that. So let's say we are, for simplicity's sake, 2 meters away from our friend, but we are 20 meters away from the tree. It's going to be really nice. Right? It's going to be really easy to tell how tall this tree is. It's very tall, actually. Okay, so we've got that triangle, and we can label all the sides in the known angle. Okay, this angle, we don't know what it is. But we do know something about it. If we call this angle beta, okay, then theta plus beta plus 90 degrees would equal 180 degrees. Okay, and removing the 90 over there, theta plus beta would be equal to 90 degrees. Okay, it's just subtracting 90 from both sides. So theta and beta are both there. And in the bigger triangle, let's go ahead and draw our bigger triangle over here. We'll use green because the tree is involved. So that's angle theta. This is also 90 degrees. This was 20 here, and we don't know x yet. What about this angle? Well, theta plus 90 degrees plus that angle must equal 180, so it must be the same as beta. Okay, it's also beta. Because we have two triangles that have the same angles, we know that these triangles are similar. That means the ratio between the sides is the same. Okay, and if we look carefully, we can see that this side length is 2, this side length is 20. So this triangle is 10 times as big as that triangle. So I expect x to be 10 times as tall as my friend here, 1.5 meters. A rather short friend, a rather tall tree. Okay, but if we had more complex numbers where I can't just do it in my head very easily, this is what you would do. You would say, let's put together this as a ratio. So we're going to say 1.5 divided by 2 will be the same as the corresponding sides in the similar triangle divided by one another. X divided by 20. Okay. Now to solve this equation, we multiply both sides by 20. That cancels the 20 on the top and the bottom there to give you an equation just equal to x. X is the only thing left there. 20 times 1.5 is 30. 30 divided by 2 equals 15. So we now know, therefore, the tree is 15 meters tall. And we can use similar triangles to solve those types of situations. Isn't that cool and useful? Yeah, surveyors do this kind of stuff a lot to measure things that would otherwise be very difficult to measure. So let's keep going. So here we had these two over. Yeah, we just talked about all of those.
I'm back.
Oh, great. One moment. Okay, back. So yeah, so we've solved that. So let's keep going. And then here, we can also use the sides of triangles to show that they're similar. Okay, there's two things that you can do to prove that triangles are similar. One is to show that all the angles are the same. Then you know that the shape is the same. If the angles are the same, the shape is the same. And then if the ratio between the sides is the same, then that must mean that the angles are the same and that they're similar. Okay, so if one or the other is true. So let's take a look at this example here where a surveyor is measuring this river.
This one doesn't look very good.
Zara, I know about the bananas, okay? Just go to your class. Sometimes they need a little firmness to be reminded to stay where they need to be. Okay, so here, this one 5, this one 3, this one 4, 15, 20, 25. So let's analyze this and see if these triangles are similar. So we have a river, and we're going to use blue to represent our river here. And it's very hard to measure across the river. So the surveyor has what they have done is they have sighted across the river like that to a mark right on the side of the river, and then this comes across here, and then this one, and this one. Okay. Now, this angle here, and then what they do is they measure 90-degree angle. This is easy to measure. It's on this side of the river. This is easy to measure, and this is easy to measure. They can measure all of these things. They can also measure this side, but they can't measure that side and that side. Okay. Now, hold on one moment. Yeah. Okay. So, right. So then we've been asked to show that these triangles are similar by working with the side lengths, but I'll show you in a second how you can prove that the angles are the same. Okay, so let's add some labels for the length of the different sides. So they said this one was 4, this one was 3, and this one was 5. Okay, and then they said this one was 20, this one was 15, and this one was 25. All right, so let's label our sides. Well, let's label our triangles. When we're labeling triangles, we label the corners with big letters. Okay, so capital letters. So this is A, this is B, and this is, for this triangle, C. And then for this triangle, this is A prime, B prime, and C prime. Okay. They're arbitrary. You can choose whatever letters you want, but A, B, C are very common. These are the first 3 letters of the alphabet. Okay. If we can show that that length A, why is that so giant? Hey, be that one. Thank you. Okay. Sorry. Thank you for your patience as I struggle with my technology. That AB, this length over A prime, B prime is equal to, well, the other ratios, B prime, C prime, and A prime, C prime over B, C, and A, C. Okay. If these are all the same, then the triangles are similar, and we'll find that they are. Watch. AB over A prime, B prime, well, that's equal to the ratio of the other sides. AB is 4, AB is 20. So 4 over 20 gives us 1 over 5. Let's write it out. This is 4 over 20 equals 1 over 5. Okay. We're also going to find BC. So here's BC, 3 and 15. Okay, so let's put those in. 3 over 15. Well, that's also 1 over 5, just in a different form. And then this one, 5 and 25. That's 25. And that's 5. Well, all of these are equal to the same thing. They all reduce to the same thing. So these triangles, therefore, are similar. Okay. Now, that's really useful to a surveyor because they can measure the length of across the river without having to swim, okay, by creating these triangles. Why are these triangles similar from angles perspective? This angle here is the same as that angle there. Okay. Why? Because this line is parallel with that line, and this is a transverse crossing it. And we have our F pattern here. You just have to see that the letter F is upside down like this. Okay. And that the letters, the angles in the corners are the same. Because this angle is the same as that angle, and that angle is the same as that angle, then this angle here will be the same as that angle here. Okay. So that's why those triangles are similar. And we see one of the applications of similar triangles here. Come on, zoom out. There. Okay, now they've done the same thing here. They just did the fractions in different orders.
Hey, hello. Okay,
Hooey, so popular. Okay, so yeah, we're done that. So now, this is the key ideas, and these are important to read and to maybe build into your notes. Congruent figures have the same shape and size. They are the same. They're effectively the same. They could be rotations of one another or flipped versions of one another, but if they have the same angles and the same length of sides, then they are congruent. Okay, similar figures can have the same shape but different sizes. So if these are similar triangles, then C over V would be equal to A over T would be equal to B over U. All of those ratios of corresponding sides would be equal. Okay? Yeah. So that's the key idea there with similar triangles. We can use these similar triangles to solve problems. For example, here in this example, it's just the same idea as what we were looking at with having your friend stand there, because these will create, these shadows create similar triangles. Why? The angle of the sun creating this triangle, the sun is up here somewhere, okay? And it shines down and it creates an angle with the ground. That's the angle of the sun. The angle of the sun here is going to be the same as the angle of the sun there. Because these are 90-degree triangles, these students are carefully holding the meter stick up at 90 degrees to the ground, and the tree is 90 degrees to the ground. Then we have similar triangles. We can measure this, and we can measure this. We can also measure this, but we're not squirrels with tape measures. We can't measure this. But we can find it, we can solve for it using the power of similar triangles. Isn't that exciting, everybody? The geometry of similar figures is a powerful area of mathematics. Similar triangles can be used to measure the heights of objects that are difficult to get to, such as trees, tall buildings, and cliffs. They can be used also to measure distances across rivers and even galaxies. Isn't that cool? We can use similar triangles to measure things that are super, super, super far away. So very important to astronomy. Okay, the students in this photo, blah, blah, blah. I've already talked about that. Okay, so how can you apply the problems to solve this? Look at the illustration, discuss with a partner. Sorry, I already gave it away. Yeah, so the thing you do there is you realize that these triangles are similar and you can measure all the sides of that very easily. You don't need to measure the hypotenuse though. You can just measure this. And then you'd only need the hypotenuse if you wanted to know, like, I'm standing there and I have a certain range with a slingshot and I want to
Hello.
hit the squirrel up there. One moment, I'll
I'm
be
back.
right back.
Okay, I think I got the answer.
All right, it's just us now. It's lunchtime, so I can finally finish up for you guys. Oh no, it's the scary grade 11 stuff again. All right, so we've talked about that. We've talked about that. Let's go here to see what we're talking about. Oh, more grade 11 stuff. Oh my goodness. Leave. Turn that off. Turn this off. And where were we? I haven't talked about that. Oh, we've talked about this. Okay. So, yeah, so we had a strategy for that using similar triangles. Now, the scale factor is a useful quantity when working with similar triangles, such as these ones. Okay. The scale factor is the factor that relates the corresponding side lengths of two similar triangles. So here we have a 2, 4, 5 triangle and a 6, 12, 15 triangle. I know this side corresponds with that side. The shortest side corresponds with the shortest side, and the longest side corresponds with the longest side. Here, the factor k is 3, okay? Because here 5 got scaled up by 3 to become 15, 4 got scaled up by 3 to become 12, and 2 got scaled up by 3 to become 6. So if I know the scale factor, that's really useful for when I'm solving, again, one of these problems. So if I find the scale factor, I can solve this, okay? So here we want to know the length across the river. So the way we do that is we find the scale factor. We know this side, and we know it's the corresponding side to that side. Why? Because this angle here is the same as this angle there because of the Z pattern. Okay, so that means I need to rotate this triangle around so that this corner corresponds with that corner. That means this side corresponds with that side. The hypotenuse sides correspond with one another, and this side corresponds with that side. Okay, that's why these two sides correspond. So I divide 24 by 9.3, and that will give me the scale factor of these two triangles. Then I can just multiply 8.4 times the scale factor to get this. Okay, let's see what they did. Okay, so they showed which two sides correspond, and then on the next page they carry on. And so then they're going to find the scale factor. So they did BM divided by BS. That's what I told you to do. 24 divided by 9.3. Okay. And now each side in the larger triangle is this much times as long as its corresponding side in the smaller triangle. So leave the scale factor in that form for more accuracy, and then you can do your calculations, okay? So if I want to find WM, I just multiply the scale factor by the corresponding side in the smaller triangle, which was 8.4. And that gives us the answer of 21.6 repeating. So 21.7 is fine. But if we wanted to round the answer to the nearest meter, we would say that it's approximately 22 meters across the river. Okay, cool, right? So the scale factor is a very useful idea for comparing different triangles that are similar. And then the last idea here is that be careful when you're looking at area, because it does not correspond exactly to the scale factor. And let me create, well, here we can show that these two figures are similar and find their scale factors, okay? So 3, 4, 5 is a triangle, and 6, 8, 10 is a triangle. The scale factor here is 2. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. Therefore, the triangles are similar because the ratio of corresponding sides is always 2. And we can use that to then find the area of this one, the area of that one. Okay, so now let's compare that to their areas. And I'm just going to go over to here and create these triangles. Here is 3, 4, 5 triangle. Oh, that's a terrible triangle, Mr. Jennings, but we want to go fast because we're already way too long here. 3, 4, 5. And then we know that there's this other triangle here, 8, 6, 10. Okay, 10, 8, 6. Note that these are right angle triangles because 3 squared plus 4 squared does in fact equal 5 squared. Test it for yourself. And this is called a Pythagorean triple as a result.
I'm done.
Good, I'm not. I'm not done, Zara. So please let me finish.
My mom comes back at 9:30.
Okay, great. Not 9:30. Anyway, thank you for your patience during the interruption. Maybe you're more patient than I am, or maybe you're not. I don't know. I can't see you right now. You're watching a video after all. So anyway, this one here, similar to that one there. Let's find their areas. The area of triangle 1 is equal to 1/2 the base times the height. Well, we can use 4 as the height because it is indeed a right angle. That's the condition you need, is that the height is right angle to the base. So this is equal to 1 over 2 times 4 times 3. Okay? And then you will see that this is 1 over 2 times 4 is 2. 2 times 3, this is equal to 6. Okay? So the area of this triangle is equal to 6. Let's find the area of this triangle. Do you think it's going to be 12? That's a reasonable assumption, and you're not correct. Okay, that's wrong. Okay, that's the mistake we want to avoid. You can't scale up using the scale factor. You have to use the square of the scale factor. Let's prove it to you. Okay, here the area of triangle 2 is equal to 1/2 the base times the height. Okay, this is equal to 1/2 times the base here, 6, times the height there, 8. 1/2 times 6 is 3. 3 times 8 is 24. So the area here is 24. Why didn't that just double? Because I could write this triangle in another way. I could write this triangle like this. 4 times 2, 3 times 2, and 5 times 2. I didn't change anything. I just wrote all these numbers in a weird way. I'm 21 times 2 years old. It's the same thing as saying I'm 42 years old. Okay, it's just weird. Now, this is similar to that because we can literally see the scale factor in all the spots. If I calculate the area of this triangle, it's 1/2 times 4 times 2 times 3 times 2. Notice that it's the same as this, 4 times 3, 4 times 3, but I'm multiplying by 2 twice. I can write this again as 1/2 times 4 times 3 times 2 squared, because there's 2 times 2. 2 times 2 equals 2 squared. So when you're comparing the area of similar figures, you want to have, see smaller triangle area 6, larger triangle area 24. So the area of larger triangle is 4 times the area of the smaller triangle. The relationship holds for all similar figures. The ratio of the areas of two similar figures is equal to the square of the scale factor. If you had similar shapes that were 3D and you knew the scale factor that you scaled up the sides, the area, the ratio of their volumes would be the cube of their scale factor. So that's the way you can extend into 3 dimensions. You can also extend that into 4 and 5 and 8 and infinite number of dimensions if you're a multi-dimensional creature. Okay, let's carry on. So we can use that to solve for situations like this, okay? The shaded area is going to be an industrial zone, and we know that this area over here is similar to that because these two angles are the same, and King Street is parallel to King and Queen. They're parallel in that all the streets in the track are straight. So the railway is straight, Main Street is straight. That means these opposite angles are the same. This is parallel to that. That tells me this angle is the same as that angle because Z pattern, chung, 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 this angle and that angle are the same, and this angle and that angle are the same. So this shares all 3 angles with that, so therefore they are similar. All right. If we know this, then we can find the area of this figure very easily. And then because we know that this is 3 and that's 1, we can very easily see the scale factor. Okay. So we identified 2 similar triangles. Good. We're going to find the scale factor. This is 3. This is 1. So the scale factor is 3. All right. Now find the area of the smaller triangle. 1/2 times 1 times 1.4. Where did they get those numbers? This is 1.4. This is 1. This is height. This is base. Okay. So that's where that comes from. And then you plug that in, you get the area of that is 0.7. Okay, if I want to find the area of the bigger triangle, I take the scale factor and square it. So 3 squared is 9. 9 times 0.7 is 6.3. So the area of the industrial zone is 6.3. That's how you'd use that to solve various questions. All righty. And then, yeah. So then we have a few more definitions to look at in here. This is going to be fairly quick. Okay, so here, let's take a look. Angles of depression and elevation. These are definitions that we want. Angles of depression, when I was talking about the plane looking down at you, that's an angle of depression. It means an angle below the horizontal. Okay, has nothing to do with your state of mind. Okay, but if anyone is feeling more depressed than normal because of distance learning and you feel that you need help, definitely contact me or an adult that you can count on to have these kinds of conversations, whoever that may be. Angles of elevation, on the other hand, are looking upwards. They're not angles of optimism. Okay, they're angles of elevation. So this is looking up. If you were looking down from this building and someone was looking up at you, the angle of depression would be equal to the angle of elevation because this line is parallel with that line. Horizontal is parallel with horizontal. Okay, if we want to solve a problem like this, where we know that Kim and Yuri live in these parts, yeah, so we're going to use those. Oh, this is for another day. Yeah, we're not reading this today. Oh, thank goodness. All right, so that's it for today. You'd also know about angles of depression and elevation, but we're going to cover these 2 pages on a later day. Okay, this is actually several lessons in the future. I'm surprised I got it's lunchtime. I need to take a break. So there's your textbook read aloud for everyone. I hope that helps you have a more productive learning experience. And I definitely look forward to seeing you all in about 40 minutes when we all meet for our morning meeting, everyone. So welcome back. Thank you for showing up for your learning. Any questions, hit me up by email or here in the chat. Bye now.